So when we start looking at motion that maybe moves forward and backwards and speeds up and slows down, that's called complex motion, right? We're doing more than one simplistic thing from A to B. Now we can start using a graphical representation for that. So we're going to start to be able to tell just by looking at a graph, is an object going forward? Is it going backward? Is it going fast? Is it going slow? That kind of stuff. We're going to be able to look at that and visualize that. Okay. We talked on that first day about motion diagrams. This is an example of a motion diagram. Okay, this tells us about an object's motion. Okay, anything that can give us a representation of an object's motion would be considered a motion diagram. Right, shocker. Okay, so we're going to start first by looking at a position versus time graph. And you have one drawn out there. You don't have to sketch this one out or anything. But this is what we're talking about. On every position versus time graph, time is the independent variable, okay, because it's at regular intervals. Right? We're looking at the time at regular intervals. We don't necessarily control time, but we get to look at what time intervals we're talking about. The position is what is changing. So it got cut off on this graph, but that's our displacement or distance. Okay? And so distance or displacement will be measured along the y-axis. Okay, so what is distance or displacement usually measured in? Meters. Good. Yeah, meters. Okay, so it got cut off of this graph, but usually it will tell you what it is and what it's measured in. So time is usually measured in seconds. Okay? So in this particular little example of a graph, after 1/2 of a second, how many meters have they moved? 1, right? And after 1 whole second, how many meters have they moved? 2, right? They're moving at constant velocity because for every time interval, they've moved the same amount of distance. Okay, that would be what we consider constant velocity. All right, and we're going to look at that a little bit more here. Tell me now, are they moving in the positive direction? Are they moving forward or are they moving backward? They're moving forward, right? They're moving away from their starting point in the positive direction. So if our graph looked like this, would we be saying they're moving in the forward direction or the backward direction? Backward, right? They're moving from 6 meters away to 5 meters away to 4 meters away to 3 meters away, right? They're moving backward toward their to their starting point again. Okay, and we'll get into that a little bit more, but the slope of the line can tell us, are they moving forward or are they moving backward? Okay. Okay, so when we look at a position versus time graph, we're essentially looking at the displacement of that object versus the time that it takes to move that displacement. The slope of the line tells us velocity. Okay, it tells us velocity. So I don't know if I left a blank for you on your handout or what, but did I write that in there? Okay. The slope of the line tells you velocity. So the equation for velocity that we know is what? Distance over time. Good. Velocity equals distance or displacement over time. Okay, so when we find the slope of the line, what's the equation that we have for a slope of a line? M equals, good, change in y over change in x. So look at how that connects to your graph. Okay, change in y, what's sitting on the y-axis on a position versus time graph? The distance or the displacement, right? And what's sitting on the x-axis on a position versus time graph? Time, right? So that's where that equation, that parallel comes from. To find velocity from a position versus time graph, all we do is calculate the slope. We're finding out how much distance did they cover in a certain amount of time. Okay? So I think I have a graph on this slide for you to look at. Okay, so let's go ahead and calculate the velocity of this object. We already talked about, this is the same graph that I just showed you. They're moving 1 meter every half a second. So how many meters do they move every second, every full second? 2. We would assume 2 meters per second, right? 2 meters, 2 meters after 1 second. So let's calculate the velocity and see if it matches what our graph is showing us, okay? So to calculate the slope of a line, what should we do? Pick 2 points, right? So we could pick any 2 points. So I'm going to pick 2 points along this line. Okay, realistically, it's most simplistic to pick the origin if you can, but I'm not going to today. Okay, so do this along with me. Calculate this along with me. If you don't have your calculator out, go ahead and grab that, please. I know that we know what answer we're getting here, but I want you to see it plug in. Okay, so we picked any 2 points along this line, and we're going to find the slope of those. Okay, so slope is change in y over change in x. What'd you say? Ooh, sorry, you're right. Thank you. 2.56, you're right. Thank you. Oh, wow. Okay. All right. Yep. Thank you. Okay, so now we can do change in y, hopefully with the right numbers, over change in x. So our final y was what? Good. And our initial y was 1, 5, and 1. Right, on the y-axis, we agree there? Our x is going from 2.5 to 0.5. So, oops, that's going to be over 2.5 minus 0.5, which gives us 4 over 2, which simplified tells us our slope is equal to 2 meters per second. Okay, isn't that what we predicted? All right, we saw that on the graph. So that's our slope, which means that's our velocity of our object. Okay, so anytime our position versus time graph has a straight line, that means, a straight slanted line, right? A straight line on a diagonal at any sort of degree, right? Any sort of slope means it's moving at constant velocity. Okay, so we didn't see any speeding up or slowing down happening here. This was extremely regular, right? Every 1 second they covered 2 meters. After 2 seconds they'd covered 4 meters. After 3 seconds they'd covered 6 meters. Okay, so it's extremely regular. Every time we have a straight line, a straight diagonal line on a position versus time graph, we have constant velocity. Okay? Are we agreeing or seeing it? Yes or no? Okay, so slope of a position versus time graph tells us velocity. Okay, we're going to learn about 2 different types of graphs, so you have to know what the slope of each of those graphs tells you. Okay, so if you are unsure, think about literally when you find the slope, right? This would be displacement over time. Okay, and what equation does that look like? It looks like velocity. Okay, so that's where you're going to try to remember that. Okay, on this next graph, we have a little bit more complex time, right? It's not just constant velocity in the positive direction. Now we're moving all over the place. Okay, so we're going to just talk through what's happening in this, and then we'll be able to solve a few things here. Okay, so on this position versus time graph, for the first 2 seconds, what's the object doing? It's standing still, right? Its position is unchanging. It's standing still for those 2 seconds. From 2 seconds to 5 seconds, what's it doing? Going down or backward, right? And is it moving at constant velocity? Yes, because it is a straight line. Okay, it's pretty quick velocity because it's a pretty steep line, but it's moving at constant velocity for those 3 seconds. Okay, from 5 to 7 seconds, what do we see we're doing? Going forward. What's it mean that we cross the x-axis? Exactly, you're just hitting your starting point again, right? So we've gone backward and we're going to go forward past our starting point. Okay, so we're just kind of moving back and forth here. Good. From 7 to 12 seconds, what's happening? You stand still, you stop. Okay, so a horizontal line on a position versus time graph tells us we're standing still. Okay, standing still. From 12 to 14, what are we doing? Moving backwards. And are we going backward pretty quickly or pretty slowly? Yeah, fast, really quickly, right? We're covering a lot of distance in a short amount of time. So we're going quick, right? If you were just comparing the speed of these two portions of time, which one would move faster? would you guess? Between this one and this one, which one is moving faster? The second one, right? The longer one. It's got a steeper slope. That means we're covering more distance in a shorter amount of time. Okay, that's what we're looking at. Here to here, what are we doing?
Forward.
Moving forward again at constant velocity. Then we're doing what? Standing still. Moving forward, and then standing still. Right, we're back to our starting point. Not all position versus time graphs will end up like that, where you're back at your starting point. Okay, that just happened to be the case here. Okay, so if you viewed this graph on your own, would you be able to talk through the motion like that? Tell me what's happening. It's moving forward, it's moving backward, it's standing still. Okay, that's the starting point.
The y-axis be distance or displacement?
Displacement. We're talking about how many meters we are from our origin, from our starting point. Okay. Okay, so now, I don't know if I give you another graph. Okay. Looking at this graph right here, let's just do a couple practice with this, okay? So if I asked you, this is how the question might be worded. What's the velocity? Oh my, okay. What's the velocity from 12 seconds to 14 seconds? Right, find the velocity from 12 to 14 seconds. So what does that automatically mean that you are calculating? The slope, right? All you're doing is finding the slope of that line.
Velocity equals...
That's right. On a position versus time graph, velocity is slope. Okay? So calculate the slope of that line. I think you can do that on your own. Are the negatives here important? Yes, they are important. Right, because they're telling us direction. So that negative is very important. Why did this velocity come out negative? It's going backward, okay? So when we're looking at the slope of a line, that anytime our slope is negative, right, that means our velocity should be negative. Okay, that seems really simplistic, but you need to understand anytime our slope is negative, that means we're moving backward. Right? So our slope is negative 4 here. After I did the math for the second time, I got negative 4, okay? But that's telling us that for every second, we're going backward 4 meters. Okay? That's what that's telling us. Okay, so if I asked you, what's your displacement? What's your displacement from 3 to 4.5 seconds? What would you tell me? What's your displacement from 3 to 4.5 seconds? Hey, you're not moving, right? So you're at 60 meters, right? Your displacement is 60 meters because you're at 60 meters from where you started, and you're not moving during that time. Okay? Uh-huh.
Displacement's the thing where you went around the room and ended up at the starting.
So how far you are from where you started. Yep. Okay, so if I were to ask you what's the velocity from 0 to 1 second, what would you tell me? From 0 to 1 seconds, what's the velocity? 0. Why 0?
Because you're not going.
We're not going anywhere, right? We started at 20 meters. We're still at 20 meters after that 1 second. Okay, so don't let questions like that freak you out. Okay, if I were to ask for what's the displacement at 2 seconds, right? All you do is displacement at 2 seconds, you just read the graph, right? I'm 40 meters away from where I started at that point. Okay. Technically you started at 20, but we're talking about from the origin. Okay. What's the velocity from 4.5 to 6 seconds? Go ahead and calculate that. What's the velocity from 4.5 to 6 seconds? And we're going to look at these two different types of graph. Position versus time is the one that's on the top. Okay, we see a constant change in position, which means constant velocity, right? Anytime we have a straight diagonal line, we have constant velocity. So, believe it or not, these two graphs show us exactly the same motion. Okay? Position, this one's not on your handout, I don't think. We're just talking through what the difference. Position versus time is how many meters we're changing over a certain amount of time. A velocity versus time graph is telling us at the rate at which our velocity is changing. Okay? We're telling us how fast our velocity is changing over a certain amount of time. So, since we know this is constant velocity, if we look down here at our velocity versus time graph, this straight line horizontal is telling us that we have constant velocity. Okay, so we're going to dive into these bottom types, these velocity versus time graphs, next. Okay, but we need to understand that right now these two graphs represent the same motion. Okay, and if we were to calculate the slope of this top position versus time graph, we would see that it's moving at 200 centimeters per second, which is what this line is showing us. Okay, so let's dive into velocity versus time graphs a little bit more. These graphs represent for us non-constant velocity. Okay, and I don't know that these are on your slides yet either. Okay, so we're just kind of following along for right now. These are non-constant velocities. So this means we're looking at cases in which objects are speeding up and slowing down. Okay, they're not just moving forwards and backwards at constant velocity. They're getting faster or they're getting slower. Okay, does that make sense? The difference between those two? So this is non-constant velocity. So let's take a look at walk through what's going on here. From A to B, we're going from 0 meters per second to 20 meters per second. So what are we doing? We're speeding up, right? We're going faster. And are we going in the positive direction or the negative direction? Positive. Okay, this is a little bit tricky, but on this graph, we don't see any negative velocity, right? Negative velocity would be below the x-axis. So for this whole situation, we're going forward. And that's going to be hard to understand, especially when we have a negative slope, but we're going to talk about what that means. Okay? So right now we're speeding up in the positive direction from A to B. Yeah?
You said like you don't have negative velocity, but if you would do the slope from E to F, would that be negative?
It would be negative acceleration, but still we're moving in the positive direction. We're just going from 40 meters per second that way to 20 meters per second that way. So we're just slowing down. Okay? Yeah, that's tricky. Yeah?
So does it take time to like get moving at the movement? Like how does it, or does it just go, because it's not constant now.
Yeah, it's not constant velocities.
Dead still, so wouldn't it take a little bit for it to get, does it get going faster the longer it gets?
Mm-hmm.
How do you know?
Right, our velocity is going from 20 to 21 to 22 to 23, like that's the speeding up right there.
How would go from like 4 to 5, it's going slower than it would be going from, it's hard on that graph because it's so small.
Okay, all right, Griffin, what do you got?
How do you have a negative velocity? Like if you're going in reverse, almost like in a car. Okay, I was just trying
That's
to
the negative velocity, that's right.
Because I was thinking you still like speed up. Or you're
Yeah, you can go, you can have a negative velocity. So if I go from 0 meters per second to negative 10 meters per second, I'm speeding up, but I'm going in the negative direction. So the negative that goes along with that number is telling us only direction, not the size of the number. Does that make sense? That negative doesn't have anything to do with the size, the magnitude. That's where it gets tricky because the negative is no longer really attached to the number like it is in math. It's more attached to the direction. Okay? All right, so let's finish walking through here. From B to C, what's happening?
It's standing still.
Is it standing still or is it moving at constant speed? Yeah, that's where it gets really tricky, right? Everyone wants to say it's stopped right there, but it's not. It's moving constantly. So that's cruise control, right? We've sped up and we set our cruise control for that 2 seconds. Does that make sense? Okay, all of you on your first quiz or first test will want to put they're standing still during that time. That's not the case, right? We're just moving at constant speed there, okay? So from C to D, what are we doing?
Speeding up.
We're speeding up in the positive direction, right? This whole thing's positive direction. So we're speeding up, right? We're going from 20 to 40. From D to E, what's happening? Constant speed, right? We're cruise control. From E to F, we already talked about this one, but what are we doing?
Slowing down.
We're slowing down. So we hit the brakes, but we're still moving forward. It doesn't automatically mean we start going in reverse. We're just slowing down, okay? From F to G, we are constant speed, right? Cruise control. And then G to H, we are doing what? Speeding back up, okay? So now that we've looked at non-constant velocity, we can start talking about what the slope of this line means, okay? The slope of this line tells us acceleration, which is a new concept for us. We haven't talked about acceleration yet, okay? What acceleration is, what acceleration is essentially a change in velocity. Any sort of change in velocity is considered acceleration. We have this misconception that acceleration means speeding up, right? That's not always the case. Acceleration can mean slowing down too. Okay, and that's a tricky concept for us to understand. We have this misconception that anytime we accelerate, it means we're speeding up. But acceleration as a whole means change in velocity. Okay, so just keep that in mind as we're looking at these graphs. To find the slope, or to find the acceleration from velocity versus time graph, we calculate the slope. Okay, we've already learned how to calculate slope, so we do that. Okay, so the velocity versus time graph tells us acceleration. Okay, how fast our velocity is changing. It can also tell us displacement. Okay, so there's two things that we can solve for from a velocity versus time graph. We can find acceleration and we can find displacement, which is how far they've traveled during that time. Okay, does that make sense? So I'm going to show you these two things first, and then we'll go back and we'll do lots of practice with each. Okay? So displacement from a velocity versus time graph is finding the area under the graph. Okay, and this is what I mean. If we wanted to find out how many meters this person has traveled from 0 to 4 seconds, we're going to find the area under this graph. Okay, and we stop at the x-axis. Okay, do you know how to find the area of this irregular trapezoid? Right, is there a formula for an irregular trapezoid?
Is it the top two, like, and then you use the bottom two as well?
No, just
I
I don't know if there's a formula for that. But what I'm saying is we can split it into a triangle and a rectangle, right? So if there's a shape that is irregular, just split it into shapes that you do know. Okay? So let's calculate this. Let's find the area of this. What's the area of a triangle formula?
Base height or
Yeah.
times height times half.
Yeah, that's right. That's right. Any of those variations, right? 1/2 length times height. So we've got two triangles here. So I want you to calculate this along with me. Is this one on your paper?
Yeah.
This is on your handout? Okay, so let's do this one together. So right now, what we're doing is we're finding displacement. This is what we're doing. We're finding displacement from 0 to 4 seconds.
And you just add all the areas together.
Yeah, you're going to find the area and then add that whole thing together. The important thing is that we stop at the x-axis. We're not going above or below the x-axis. We stop at the x-axis. Okay? So this side of this triangle is 2. This height is 2. Okay, so that means this triangle would be 4 divided by 2, which is 2. 2 times 1, which is 2. And 2 times 1, which is 2, divided by 2, which is 1. Sorry, I know that's kind of hard to read. For this triangle, I had it at 2. For this rectangle, I had it at 2. For this triangle, I had 1. Do we agree?
Yes.
Okay. So to find this triangle, this side right here was 2 seconds times 2 meters, which is 4, divided by 2. So this triangle gives us a distance of 2 centimeters, because this is measured in centimeters per second. This rectangle is 1 across by 2, so this rectangle is 2 centimeters, and this is 1 by 2, which divided by 2 is 1. Okay, so total during that 0 to 4 seconds, we've traveled a total of 5 centimeters. Okay, and have we traveled in the positive direction or the negative direction?
All of
positive. Right? We're above the x-axis. This is where it gets tricky. On a velocity versus time graph, anything above the x-axis is positive direction. Anything below the x-axis is negative direction.
Didn't you go back to where you started?
We came to a stop right here. That's what crossing the x-axis on a velocity versus time graph means. We've come to a stop. So we went forward for a long time. We sped up. We put on the cruise control. Then we slowed down.
Oh, it's velocity.
Yeah, this is velocity versus time. So let's talk through what the motion looks like again. Any questions on displacement here? Okay. Let's talk about what this motion looks like. We didn't do that first. What are we doing here?
Speeding up.
Speeding up in which direction?
Forward.
Positive, right? And then here we're doing standing still. What are we doing from here to here? We're slowing down, but we're still going in what direction? Positive direction. When we cross the x-axis, what's that mean just for an instant? We've stopped. When we crossed it, right, for this little second that it's at the horizontal axis, we've stopped. Now from here to here, what are we doing? We're going backwards. Are we speeding up or slowing down? Good. We're speeding up in the negative direction because we're going from negative 1 meters per second to negative 2 meters per second. Right? The magnitude of that velocity is getting bigger. The negative is just telling us direction. Okay?
Where it stands, you said we stand still?
No, we have constant speed right here. We have cruise control right there. Did I say that wrong? Oh, sorry. I told you, I just need to go home today. Okay? So we sped up. We put on cruise control. We slowed down and came to a stop. Then we went backwards. For this last little section of our graph, what are we doing?
Going fast.
Right here.
Oh, which is
Slowing down in the negative direction. That's tough. Okay, this is why we know we're slowing down. We're approaching zero velocity. Right? We're approaching the x-axis. So we're starting to slow down. That's really tricky. Okay? So tell me what other, 4 to 5 seconds is here. What do we do to find the displacement from a velocity versus time graph? The area. Good. And we stop at the x-axis. So if we draw it along the graph to the x-axis, it gives us a nice triangle. Okay? So this side of my triangle is 1. This side of my triangle is negative 2. Right? Because I'm moving backwards here. We already talked about the fact we're moving backwards and we're speeding up. So when we find the area of that triangle, negative 2 times 1 is negative 2. Divided by 2, which is negative 1 centimeters. Okay, we already said we're moving backwards during that time interval, so it makes sense that our displacement is negative. Right? We're behind or below where we started. Yes, do we agree with that? Okay. Okay, the slope of the line on a velocity versus time graph tells us what? Acceleration. Okay, if that's not written in there, make sure you write it in there. The slope of a velocity versus time gives us acceleration. Okay, we're going to do a lot of practice with graphing within the next couple days, so we're going to get familiar with these, but these are things we have to know. Okay, the slope of the line on a velocity versus time graph tells us acceleration. How fast our velocity is changing. Okay, time's still the independent variable. There's nothing else on there I need you to see. Okay. Okay, displacement here from 5 to 8 seconds. Tell me the displacement here from 5 to 8 seconds. Okay, it's constant speed, so that means, are we still moving?
Yep.
Yeah, we're still moving. It just makes our displacement really easy to calculate, right? If we're moving 40 meters per second for 3 seconds, what could we expect our displacement to be? 100, oops.
I thought it was 40. Just 40.
40 meters per second for 3 seconds. So we have to find the area. So yeah, we're going to look at how many meters are we covering during that 3-second interval. So if we're going 40 meters per second, that means we're covering 40 meters in 1 second. So after 2 seconds, we would have covered 80 meters. After 3 seconds, we would have covered 120 meters. Okay? What would happen if I asked you to find the displacement of the whole graph?
I don't know.
Oh, you just have to add them all up.
That's right, you just add them all up. So you have a lot of crazy rectangles, a lot of crazy triangles, but you just add them all up. So if I asked you for the displacement from 0 to 12 seconds, all you're doing is finding the area under that graph. Okay? And in this graph, everything's above the x-axis, so we know we're moving in the positive direction the whole time, which makes it really easy. Okay? If we had graphs that went above and below the x-axis, you'd add them together and make sure you're adding your positives and taking away your negatives. Okay? We're just finding the area of the section of the graph only to the x-axis.
On the position versus time, the straight, like the horizontal line stands.
That's right. That's right. But here, this means we're just moving at constant speed, so that's cruise control. So we're still moving. We're just not speeding up or slowing down. Okay? Are we getting there?
I like the position on the
All right, here we go. Let's do some examples here. Using the graph, determine the acceleration from 0 to 2 seconds. You have to be careful and look at this graph and how it's labeled. 2 seconds is how many blocks? It's only 1 block, right? It's labeled every 2 seconds. So from 0 to 2 seconds, the displacement means we're going to find what? The area. The area. Okay, and you only go to the x-axis. Look on this graph how easy it would be to just do this on accident. Right? And find the area of that whole thing. That's not the case. We have to stop at the x-axis. This 0 goes with the x-axis. That's kind of tricky. Yeah. Okay, so 2 times 2 divided by 2, which means we traveled 2 meters. Okay, displacement should always be measured in meters. Two times 2 is 4, divided by 2, which is 2. Right, it's because this isn't just 1 second, it's really 2 seconds, the way the graph is labeled, so you got to be careful there. Okay. Find the displacement from 8 to 10 seconds. 8 to 10 seconds. Okay, still should be 2, right? It's the same size triangle. Are we still moving forward in this case from 8 to 10 seconds? Yes. How do we know we're still moving forward? Good. It's above the x-axis still. Okay.
We're just getting slower, right?
We're just getting slower, exactly. We're approaching 0 velocity, which means we have the brakes on. So 2 times 2 over 2, which is 2 meters. Okay, what's our velocity from 16 to 18 seconds? What's our velocity from 16 to 18 seconds? So right here. -2 or 0? -2. Just read the graph. Okay, so it's really, really easy for us to think we're standing still. Okay, especially when I say it wrong that one time. But on a straight line, right, a straight horizontal line, we just go over and we just read the graph. Okay, so we know we're traveling constant velocity at -2 meters per second there. Okay, do you want to do a couple more or do we feel okay? Feel okay? Okay, I'm going to go ahead and give you your homework assignment then.